Hello ladies and gentlemen, this is Dean from Awfully Pi, and we're back with linear algebra. So in the last episode we looked at solving a simple system of equations with two variables and two equations, and this solved for the intersection of the lines given by those two equations. Keep in mind that a point is zero-dimensional, and that's going to be important in a second here, but last time I asked you what would happen if you introduced some more equations and more variables, and the immediate instinct is that it would just take more time, which can be true, and it can be done using the method that I showed last time in some cases, but more often than not, you might notice that given enough variables and not enough equations, there isn't a way to cancel everything you need. So this is essential to linear algebra, namely the linear part. So is there a better way to do this just in general terms? The answer is yes, there is, and it's called the matrix, which is plural matrices. Unfortunately, this isn't as cool as some computer simulation or Keanu Reeves dodging bullets. In fact, it's simply just a list of numbers set up that you can reduce them in a similar fashion as I did in the last video. Matrices are generally denoted by hard brackets and have a shape, that is a height given by a number of rows. And there's the numbers and there's the rows. I've used P here in place of the Greek letter rho, which my professors did as a nice little pun there, and a width given by a number of columns. It's important to remember the order too, because if somebody says that they need a 3x2 matrix, they want it tall, not wide, and it does matter because they reduce differently. So how does a matrix apply to a system of equations? You have variables here, but they aren't numbers, and I said that it's a list of numbers. And this is an equation too, but equations don't fit here. So what to do? Well, just break it apart. Remove the operators and the variables, and why do the variables go? They go down here. They're reflected in the order. Oh, that's a black box. I didn't mean to have that open. They're reflected in the order of the columns. See, the first column here is X, and the second column is Y. It's common that there's a third row when applicable, but not here, as we don't have a Z variable. So our third column is actually our constant column. And here's our constants in the equations, but what do we do with the equals sign? Well, you draw a bar. Oops, that's on my selections. You draw a bar. This is called an augment, because technically the constant isn't part of the matrix. We do this ordering thing because X, Y, and Z isn't always the set of variables that we use. Sometimes we have A's and B's. Sometimes it can be alpha, beta. Generally, the terms of algebraic constants, or algebraic variables, is not really needed. Now, we're going to solve for the null space of this matrix. And right now you might say, whoa, slow down, what's a null space? It's not important that you understand vector spaces right now, just know that it represents the solution of this system. It's unaffected by row operations. Row operations, though, are important to know now, so I'll teach you about them. These are analogous to the techniques that I did in the example before, and there are three, so it's not so hard. One seems simple. You can swap the rows with each other. In the example I did this before, anything else. Notice I put the 2x on the bottom before. This isn't always the case, but it can make it easier to do some swapping first. Next, you can multiply your row by a constant, which it might seem like I did before to match the x coefficients, but that isn't quite right. I actually use the last row operation, which is that you can add multiple of another row to another. To subtract, use a negative multiple. So it's always addition, but sometimes you use negative multiples. Keep in mind, row operations apply to augmentations as well, even in the addition. So in the example before, I used all three operations. I swapped the first and second row. I added -2 row 1s to row 2. and I multiply the second row by 1/25. Now, in row reduction, which is the process of using row operations, you don't substitute a value into one of the other variables, which is where the methods differ here. Instead, you keep reducing. Up until this point, we've been doing Gauss elimination, which brings one row to one variable. Continuing is known as Jordan elimination, where you work back up the matrix. So you'd add 8 row 2s to row 1. This works the same as substitution C because we've canceled the x term in row 2. So adding 0 to something does nothing in matrices, and everything else is done in one step. 2. Now, taking the 2 out, we've reached what's called a reduced row echelon matrix, where the leading entries on each row is a 1, and there isn't anything else to reduce. And it's called row echelon because echelon is kind of like a staircase, so you see you have a little bit of a staircase shape there. Now, to find your solution, you do a little L shape. So you take this one here for the first variable, look for the column for leading 1, and look across to its augment. This tells you that the x variable is equal to 159/50, which is exactly what we got originally. And the second time, it works the same. Here we get y is equal to -2/25, which is great because that's what we got. But what if there were more variables? Well, first let's think about what an equation using x, y, and z would be. Is it a line in 3 dimensions? Well, no. See, in the xy plane, manipulating one variable forces the other to change, which is known as a function, and you should know this from algebra or calculus or whatever. Because, let's look back at an easy example. Say x plus y equals 5. Now, if x is 3, y has to be 2, because 3 plus 2 is equal to 5. If x changes to 1, y has to change to 4. This defines a line. In 3 dimensions, let's add a z here. So x plus y plus z is equal to 5. You can't find all 3 by defining 1, because say x is 3 again. What are y and z? There aren't any dependent variables in this case. Now say we define 2 independent variables, x is 3 and y is 2. That means z has to be 0. So if x is 1 and y is 4 like before, z is 0 again. So if this were a line, this would be along z equals 0. But you can satisfy the equation with other z values, like x equals 1, y equals 1, z equals 3, or x equals 2, y equals 6, and z is equal to -3. So a single equation of 3 variables actually describes what is called a plane, which is a 2D surface existing in a higher dimension that extends infinitely in all directions, and we'll look at that a bit more when we see vector spaces. So what if you had 2 plane equations? Well, a solution to the system of equations is where the equations overlap or intersect. Imagine that you have these 2 planes that aren't parallel. They don't intersect at a single point like lines do. In fact, their intersection is a line itself. Here's one that I've drawn using paint, and here is a bit more of a detailed one that I found off of Google. So, how do you express this? Well, let's set up a matrix. To make things simple, we'll just make one that is set up in an easy way. Let's say 1, 0, 5, augment 0, and 0, 1, -2, augment 0. The augment I've made 0 so that the free variables, this is our free variable here, are directly correlated to the solution. And this is something you'll see in almost all cases where you have a wide matrix, that is more columns than rows, is that you end up with at least one free variable, which is the source of an interesting fact of systems of equations. The dimension of the solution, which is the number of free variables, is the number of variables, the dimension of that the solution exists in, minus the number of equations, which is the number of objects. This is why two lines intersect at a point, because 2 minus 2 equals 0. As long as you don't have parallel objects, that is, which never intersect, this holds true to any system, and it is uncommon to see parallel objects because it doesn't help solve anything. Anyway, looking back at the matrix, this is in row echelon form, but not reduced row echelon, because there are still numbers that aren't leading ones. There's actually no way to reduce this any further, so we'll go to the L method. It's a little different this time, so watch closely. Go down the X column and see the 1. Go across, and there's a 5 on the same side of the augment, and it's equal to 0. Now, well, the augment is 0. Now we subtract the 5 and see that x is equal to negative 5z. Similarly for y, go down and see the 1, go across. There's a negative 2 on the same side, equals 0. So 0 minus negative 2 equals 2, so y equals 2z. Well, since there's one free variable, we want to define a one-dimensional solution, which is called a vector. This differs from a line because now we have a specific coordinate to apply to it. We write this vector v as x, y, z. In general, like a coordinate. But we've shown that x is equal to negative 5 and y is equal to negative 5z and y is equal to 2z. So v we can rewrite as negative 5z, 2z, and z. There's a property of vectors that allows us to pull out a common factor, as we'll see later. And you can say that v is equal to z times the vector negative 5, 2, 1. Where z is an algebraic variable, which doesn't matter anymore, so we say that z is an element of the reals, meaning it can be any number. Another way of saying this is that z is now a parameter. So the solution is the vector negative 5, 2, 1, extended to infinite length, but the coordinates still denote its direction. It's important to note that this is actually what's known as a span, and again we'll see that later, but as I thought when I started, vectors do not extend infinitely. This type of problem is often not set up with a system of equations, but as a matrix A is the letter that denotes an arbitrary matrix, times a vector x. Note that x can be confusing because we're used to x being an algebraic variable, so think of this as vector v instead, equal to vector b, where b is the augment. In this example, we have used a homogeneous system where b is the 0 vector, that is 0, 0. This is not always the case, but it isn't hard to solve if it isn't. When you have more than one vector, or when you have more than one free variable, keep in mind that you are only looking for leading ones. So the second free variable has 0 of the first free variable. So let's set up another matrix, this time using 2 free variables. So in this case, we'll do a similar matrix. We'll do 1, 0, 5, negative 3, augment 0, 0, 1, negative 2, 4, augment 0. And since we've added a 4th variable, that means that we've added a 4th dimension, and that means that our vectors are going to they'll have 4 coordinates. So if we do the L method again, you'll see that in terms of v, we'll have a similar vector, except this time we have a 0 because the first free variable, like I said, has it doesn't contain the second free variable. But then we also have a second free variable, so we're going to define a second vector, again in the general term x, y, z, w, because w is the 4th dimension. And here we just ignore the z column, or we don't ignore it, but we leave it as a 0 because it doesn't include, and solve it in the same way. So we get that x is equal to 3w, y is equal to negative 4w, z is equal to 0, and w is equal to w. Take the w out, and you get that u is equal to w times the vector, the parameter, times the vector 3, negative 4, 0, 1. And as we'll see in another video, when you have two vectors, this describes a plane, so long as the vectors are not multiples of each other, which you can tell that these ones are not, because we have ones and zeros that cannot multiply into each other, other than if it were 0. So here, again, we've showed the same property as I just described, where we have 4 variables, 4 dimensions, and 2 objects. So 4 minus 2 is 2. That means that our solution has 2 dimensions. A 2-dimensional solution is a plane.